testing a claim, not about a proportion, not about a standard deviation, but we're testing it about a mean, but this time we know that sigma is not known. Sigma is not known. What are we going to do? Can't use the z-chart. We must have to use T-chart. We must have to use the T-chart. So that's why I'm going to use this chart, which you can barely see from that far. But you know what it looks like. So, okay. The only difference here is that we find the test statistic. That's it. The whole thing is the same exact thing, except we're using the T-chart, we're using the T-statistic. Critical values, hypothesis, conclusions, all of that is exactly the same. We're just, step 4 is changing. Step 4 is changing. The sigma is not known, the sample size comes from a normal distribution, or if it doesn't come from a normal distribution and n is greater than 30, we will use the student T distribution for our test. You know that. That was from confidence intervals. So, okay, here we're not using, for proportions, this was z equals p hat minus p divided by the square root of pq divided by n. Check that. For means with sigma known, this was z equals x bar minus mu sub x bar divided by sigma divided by the square root of n. We don't know sigma. We don't know sigma, so we must have to estimate sigma. We estimate it with s. And when we estimate it, we don't know it, so we have to use an approximation to the normal, which is t. Okay. So there's our test statistic. That's what we're going to use in step 4. Okay. So here is a good claim for us. Is this the one that I want to use? No, this is not the one I want to use. I'll go to the next problem. Is this the one that I want to use? No, that is not the one that I want to use. Oh, I just did the last one. No, okay, let's go back. Yeah. Hopefully we get to edit this, but if not, enjoy. Okay, so here we go. Here's our problem. This is what we're going to use. Let's claim that the mean IQ of biology professors is greater than 118. Wow, the claim's right in the first sentence. Let's claim that the mean IQ biology professors is greater than 118. They would probably appreciate that claim. They like to be smart. In order to test this hypothesis, we went out and sampled. We wanted to test it. If it's true, then we should be able to sample it and reflect it. Sampled at 20 biology professors. We found that their mean was 120 and the sample standard deviation was 12. Use a significance level of 0.05 to test the claim. Now, I copied this problem down and just saw it just a second. If on this problem right here, you decided to say, hey, I don't know that the individuals are normally distributed, and we only have a sample size of 20, and just wrote can't do anything, fair enough. You get 100% on that point. We're going to keep doing this one, because I'm going to tell you we're going to assume that the individuals are normally distributed. But if you were vigilant enough to see this, no problem. You would have to write down, we do not know that the individuals are normally distributed, because it wasn't told to us, and our sample size is less than 20, so I don't know that we can do this. Okay, well, we're going to assume that they're normal. So here we go. We want to test that claim. So again, the claim was, yes, right here, that the mean was greater than 118. So rolling over here, we're going to say that the mean, this is step 1, the mean is greater than 118. That's what we're trying to test. That's our claim. So the direct opposite of that is not greater than, but
less than or equal.
Less than or equal to 118. Boom. That one's our claim. Claim is usually the first one you write down. It is. So H naught, H1, or HA, and that one has the equal sign in it. We're getting really good at this by now. Equals 118. We're just dropping that less than and using the equal sign of that. So this one goes down here. Sigma is greater than 118. And that one's our claim. Great. So we'll copy right down. We'll put the claim right down there. No?
Mu is greater than 118.
Sigma.
What did I say?
You
Sigma?
said sigma.
For all of it?
No, just right there.
For the record, it's 10:30 at night. Give Vivian some slack.
Thank you, thank you. Yes, mu. Mu. Yeah, mu is equal to 118 or mu is greater than 118. All right. So, hey, that's step 1. We set up our our hypothesis. Step 2 is, hey, we got to set up what our test looks like. We got to set up our critical values. This looks like a z-chart, but hey, everybody, is it a z-chart?
No.
No, it's not a z-table, it's not a z whatever. It's a t.
T-chart.
It's an approximation, but it's t. So we have to maybe come back over here to the problem and get some more info. So in order to test this hypothesis, we went out and sampled 20 people. Remember, with t, we need degrees of freedom. So what might the degrees of freedom be for a sample size of 20? Remember, the degrees of freedom are...
19.
19.
Thank you, Jason.
N minus 1.
Minus 1.
Yes. Let's bring this one back in.
Yes.
Thank you to Jason. There it is. The sample size minus 1 is our degrees of freedom. Those are our degrees of freedom. Very nice. And we have 20 in our sample size. So that's what we're going to put in over here. We'll have 20, so n equals 20, degrees of freedom equal 19. Degrees of freedom are 19. So now what we need to do is find out what our significance level was. And if you remember from the problem, our significance level was 0.05. But going back and looking at this, is this a one-tailed or two-tailed test?
1.
1.
One-tailed, and it's to the right side. So we don't need to take alpha over 2 because it's not a not equals 2. It's a greater than. So we're going to put all of the alpha over here. This is all of our error. And that is 0.05. All of it. So this is step 2 and 3. Step 2 and 3, we need to figure out what that value is. So that value comes from our t-chart. From our t-chart. Now I ask you, is this in one tail or two tails again? Is that in one tail or two?
1.
Clearly in one tail. So remember, in confidence intervals, we were always using two tails. So when we looked at this chart, this one right here, when we looked at this chart, see what this looks like.
You're good.
Good. So when we looked at this chart, we always used this one for two tails, right? But we're not in two tails. We're in hypothesis testing. We're at area in one tail. And our area in one tail is 0.05. So there is our area in one tail of 0.05. Our degrees of freedom are down here to
19.
19. Good. So that looks like 1.729. So we're doing area in one tail, and 19 is 1.729. All right, so go back up here with our 1.729, and there it is, 1.729. Remember that it's symmetric, so I'll say this. If this happened to be 0.05 on this side, you would just use negative 1.729 if it was on this side. But it's not, it's on that side, so it's positive. So 1.729, hey, we're set up. Now all we need is step 4. Step 4, we know that t, not z this time, but t equals x bar minus mu, sub x bar if you like, s divided by the square root of n. X bar minus mu, x bar divided by s by the square root of n. We have all this information. Let's take a journey back to the problem. And we have it. In order to test this hypothesis, we went out and sampled 20 biology professors. We found that their mean was 120, and the sample standard deviation was 12. The mean was 120, nice IQ, and the standard deviation was 12. So they weren't all up there. Some were higher and some were lower. But if we travel back over here, we know that the mean was 120. The mean was 120 minus what we expect mu to be, what we're assuming it to be, which is 118, divided by s, which was 12, divided by the square root of n, which we remember was 20. And go ahead and calculate that. But what you should get at the end, after a short song, is